Today we're going to talk about the inflow performance relationship for dry gas. So in dry gas, we're going to imagine we have a reservoir layer where we have a well. We're going to assume in this case is vertical, and we have this layer is filled with gas. So we are saying is that when you produce that well to the processing facilities, let's make our wellhead, our choke, then our separator. What we are saying here is, well, you're going to get simply most of it is going to be QG. Okay, you will have almost no Q oil and Q water. These are very, very small. Okay, they are similar to zero. And that's essentially not always the case. You always have some liquids flowing together with the gas. But the gas allows you actually to, the gas equation allows actually to evaluate many cases where you have liquid, especially in the reservoir, because in the reservoir it might be that you don't have that much liquids. Okay, the liquids they drop out later in the system as pressure and temperature are changing. Okay, remember that we have our phase envelope, we have pressure and temperature, and for gas will be something like this. Okay, and this is the saturated region, and this is the gas region. So usually the PR and the PWF, they are on this region. Okay, so then the approximation of dry gas is quite okay, but then after maybe when I go to the separator, then I enter into the saturation region, and then I might have some liquid dropping out, either water or either oil. Okay, this is temperature. So similar to what was done for the undersaturated oil and for oil wells, there was also people working with gas, with dry gas. And they were like two different families. I'm not sure if they spoke too much with them, but they were working on methods for their particular fluids, for oil and for gas. And they were working also on trying to characterize how, what is the performance of the inflow, of the near wellbore inflow. And really one of the earliest works, this was published in 1935, okay, which is quite early. And this was published by the US Bureau of Mines. And the two main people on this paper were on this work were Rollins and Shellhart, and they published the findings that came up to establish what could be observed as a dry gas IPR or a gas IPR. So let's see a bit what they found. So first they found that the IPR is curved. Okay, like we discussed before, PWF versus QG. So this gives you a curved line like that. Okay, not a straight line like in the case of oil. But they say, well, this equation is approximately QG C PR squared minus PWF squared to the power of n. Okay, and this n was some coefficient that they saw it varied between 0.5 and 1. Okay, they were usually changing between these two extreme cases. So I'm not going to go into the details how this was measured, but they have one advantage that in the well, remember that we want to measure is the bottom hole pressure. Okay, we need to have this PWF, and that's what you really need to characterize the inflow. Okay, but they didn't use downhole gauges, but they tried to, with some equations of pressure drop and some equations of the hydrostatic height, they tried to convert actually those pressures to surface conditions and also reservoir pressure to surface conditions. So they tried to back calculate, because assuming, well, I have essentially is gas, and gas I know a bit better how it behaves. We had not like in the case of oil that might have a multi-phase mixture. So then I tried to convert parameters from bottom hole to surface conditions, and they work actually in surface conditions. So we're not going to go too much into that part, okay, because it's interesting, but it's not what we need. Okay, the bottom line is that were using this equation, or they found that it follows roughly that equation. And really, they didn't do it in this plot, but they use a log-log plot. So let's see here on this equation, we are going to fix it a little bit. So we have PR squared minus PWF squared to the power of n, and then I take log both sides, base 10. Okay, then I end up with log QG divided by C is equal to log of this PR squared minus PWF squared to the power of n. Okay, when this happens using log rules, then I have that this is the log of QG minus the log of C equal to n times the log of PR squared minus PWF squared. Okay, and essentially then if you rearrange this function, it tells you that this equation, it tells you log Q is equal to log C plus n times log of PR squared minus PWF squared. Okay, so it's the difference. First is the square of the pressures, uh, squared of the pressure, the difference of the square of the pressures. Okay, and if you plot that equation, which is essentially the same equation that I'm showing up here, okay, this equation, this curve equation, actually it gives you something like that. It gives you that the log of QG is equal to, here you have something called the log of C, and it gives you essentially a straight line with the log of PR squared minus PWF squared. And this slope, then it will be n. Okay, then that slope. So essentially, that's what they saw. Okay, that was what they were plotting. They, didn't have Excel. They didn't have ways to plot curves. But when they plotted in a straight line, they take log on both sides and they plot it in log paper. Actually, that's what they saw. And this is essentially an example from that work, from that document that tells you what kind of results they got. And you see here is the same. It's you have here the rate, okay, in the logarithmic scale. You have the difference of the pressures in squared, and then you see it has some inclination. Okay, and that equation, well, we don't know really, so far we don't know what it has inside, but we suspect this part is related to the fluid properties. Okay, this C has probably also some fluid properties, but also essentially has a geometry part. And then we have an n, which is a bit strange that it appears. What is it that n doing here? And we see some range of variation. Okay, so for now, let's just keep that in your memory now, that that's the equation they found empirically. Okay, this is empirically. Okay, that means that measured in the field. And we're going to then go, but one thing before that, so if we have, for example, a series of points, okay, if you have a series of measured points, maybe usually we have reservoir pressure, but then we have also a few other points that were measured. Let's say you went and you made a measurement, okay, PWF and Q gas, okay. Then what you will do is that you will try to change. So if you have your equation, you know that this equation should represent fairly well your data. Okay, so in that sense, you try to change in Excel, you try to change C and N to match the data. And we're going to do an exercise on that a bit later. But essentially, we try to fit a curve that passes through most of the points. Okay, change C and N to match data. Okay, but now the next step we are going to take is similar to what we did for the undersaturated oil IPR. We are going to go and we're going to try to derive it actually analytically. Okay, what this IPR, what does it mean? So let's do that. Okay, so this is the analytical derivation And remember, we have that was the rate, okay, which was the QG. Okay, remember we have something called the volume factor. Okay, so first the equation was the velocity equal to K over me dp dr. Okay, and then we said, well, the velocity is the QG local divided by the area, which is 2 pi RH. Okay, this is, we're doing it for this geometry. Okay, here we have RW, and then we have RE here, and we are assuming this is fully perforated, and this is H, and we only have gas, so we only care about the, and this is mu G. So this is the equation we are trying to solve. We want to integrate. And then one thing also we need is we need the QG. Okay, we say, well, what is the put everything in terms of standard conditions rate, because that's what we are using typically. So we want to put QG as a function of QG, okay, at standard conditions. And we know that is if we take some gas container, okay, at any pressure and temperature, and then we take it to surface, and we take it to standard condition pressure and standard condition temperature, we're going to end up with actually quite a huge volume. And we can define the volume here, the Vg, and volume here at standard conditions. So the ratio between these two is the Vg. Okay, it's Vg divided by Vg at standard conditions. This is the gas volume factor. Okay, and this is at any P and T. So this is Vg is a function of pressure and temperature. Okay, so similarly, you see that this Vg, then we know that Vg is equal to Qg divided by Qg at standard conditions, and then we can say simply that Q equal to Qg times Vg. And typically this value you see, because here is more evident than in oil, but in this value, this one is usually much larger than this one, so this Vg is very small. Vg is typically maybe something 1 e to the minus 2 all the way to e to the minus 3. It's in that order of magnitude. Okay, so after we have that, we can substitute again back into our equation, Qg times Vg. So the Vg, we put it here. This is K mu G dp dr, and on this side we have 2 pi, maybe the h we put here, r, and also the 2 pi, and the r stands just here alone. Okay, remember similarly what we have done previously, we integrate this equation between Rw and Re. This is between PWF and PR. And remember, this is a bit of an approximation because remember this rate is not actually that constant with radius, only when you are in the steady state. But actually this luckily it gives a good solution for even if this is not fully even if this condition is not fully fulfilled. Okay, so we end up actually with an equation which is very similar to our oil IPR. So we have the ln of Re divided by Rw plus minus 0.75. This is pseudo steady state. Okay, for pseudo steady state, we have all of that part down here, and we have 2 pi kh, and then we have this integral which is of Bg mu g dp, okay, from PWF to PR. That's now the main, but you see the geometry part is actually almost the same. It's actually the same as the oil, undersaturated oil. Okay, but this is the part now, this integral on the fluid properties is the one that now we have to work out how to do it. Okay, so one thing we can do here is we can, well, try to say, how do we define this BG? Okay, because if we have an expression, we can simply, the behavior of BG with pressure, okay, it's something like that at temperature constant. It's something like this. Okay, when I increase the pressure, that means that this volume here is becoming smaller and smaller, and that's why the ratio is becoming smaller and smaller. And if I come closer to this pressure, to surface pressure, then the ratio is going to be bigger, okay, because the ratio is going to be closer to 1. Okay, but essentially it has some behavior like that. So instead of coming, and the viscosity of the gas, it follows a bit of a similar trend with pressure. Okay, it has a trend something like that. Okay, increasing, going up. Because again, you're packing, you're putting more molecules one next to the other. There is more friction between them, and then it causes more shear when it's flowing. Okay, so we can do that and integrate that, but let's say, well, that BG, actually we want to find an expression, well, for BG, okay, because we're talking about dry gas and we have already some knowledge about how gas behaves. We want to calculate a bit better that BG if I can take some things out of the equation, okay, if I can do okay, so let's say we have QG at standard conditions. And we are going to do mass conservation in terms of volume flow, mass conservation. So is the rate of gas at standard conditions times the density of gas at standard conditions is equal to the rate of gas at local conditions times the density of gas at local conditions. Okay, that is simply saying in our system, in our wellbore, is simply saying that whatever flow I have here, okay, I should have a mass conservation. Everything that is coming out here should be what's coming in here, okay, or at any point at pressure and temperature. Okay, so I end up with uh, that the BO, okay, you see here it comes up this BO, QG divided by Q gas, okay, at standard conditions, this BG is actually equal to density of gas at standard conditions divided by the density of gas. Okay, is the inverse. Okay, so but how do we define the density of the gas? For that we know something, we know the real gas equation. That it simply says that P times or divided by the density is going to be equal to RT, okay? When the R is the universal gas constant divided by the molecular weight. And I'm missing something, which is the Z, okay? I have a deviation, this is the gas deviation factor. Okay, so I can say, well, my density now is going to be equal to, according to this equation, is going to be equal to the pressure divided by ZRT. Okay, and I have to say, so this equation, I'm not sure if, I hope you remember, all of you remember where it come from, but this was a development throughout many, many years. Okay, that you have here some important people. You have Boyle and Hooke. Both were English. I think Boyle was actually maybe more Irish um, so then you have Hooke, then you have some French, Charles and Gay-Lussac. You have Avogadro, who was Italian, and all of them came to the development, finally doing different things, comparing volume expansion with pressure, temperature changes. They came up with some equation like that. Okay, that where you have this Z factor is calculating the deviation from ideal gas. Okay, this is deviation from ideal gas. Okay, then you have to use consistent units here for this, RU, MW, And then let's talk a bit about set. So these were the guys developing that equation, but then set, the deviation factor, the version that we use now, comes from two big giants in the oil industry called Standing and Katz. Okay, and this was published initially, or the way we use it currently in the industry. This came originally from a paper from these two guys. Okay, this was 1941 for the New York meeting. Okay, density of natural gases. And here I put the names, the pictures, the photos of these two guys. Okay, which I think you should also keep into account. During this course, I'm just showing you some images of some giants in the industry, and these two are very important. Okay, so Katz, he was a professor at the University of Michigan, and he was actually quite a young professor. He was maybe my age by the time they published this paper, and then Standing, he was his PhD student, and he actually defended in 41, completed in 41. And I guess, I'm not sure, but maybe this is part of his PhD dissertation. So that tells you that not people that do PhD things end up in a drawer, nobody's using it. Okay, this made the base of these guys came with the equation, the development of the equation that we can use, and then these guys came with the set, with a way that the petroleum engineers can use to compute set. Okay, so in that publication we have this chart, and one problem with the set factor is that, so here you say set, and then you say a temperature 1 constant. Okay, and with pressure it had a behavior something like that. Okay, then you run for another temperature, maybe had something like that for T2 and so forth. But then when you come for another substance, okay, let's say this was for methane, okay, this was for C1, but then when you came with another substance, okay, let's say air, actually it followed a very different at T1 at the same temperature, T1. It followed a very different trend. So it was difficult to try to unify that. How do I calculate this set for all of these different substances? Okay, so it was something very clever that was done. So I say that what I first do is I say calculate some reduced temperature, which is the temperature divided by the temperature of the critical point of the substance, and then the reduced pressure, which is the pressure divided by the critical pressure of the substance. Okay, and if I do that, actually the chart, all of the curves overlap with them. Okay, so if I do that, if I divide these two parts, then you see that the reduced curve for T1 for air and methane, they're actually going to fall one on top of the other. Okay, or here I picked air, but maybe it's not the best example. I maybe use, for example, ethane. Okay, so you see that what Standing and Katz provided to the industry was this chart. Well, first for your substance, you have to, becoming a bit too small. Okay, well, first, what you have to do is you have to first, for your mixture, find these critical properties. So you need to have this critical pressure and critical temperature. And then I come to the chart. Let's say I have 10. Okay, and then I go to my critical reduced temperature. Let's say it's 1.2. And then I just go to the left and I find that is like 0.58, okay, or 0.56. That's my deviation factor. Okay, so we are going to use this chart, but actually not in the shape of this chart. Some people came and converted to an equation that it will be much easier to use for engineering calculations. Yeah, one thing I have to say here on this chart, how it is read. So this upper part of the chart is read on this axis. So let's say if you have the reduced pressure of 5, okay, then you read it up to here and 1.2. But if you have a reduced pressure of 10, then you have to read it on this chart below. So I made a mistake before. 10 is not read here, but it's actually read on this bottom part of the chart. Okay, so also we know that the critical properties, PC and TC, okay, if you remember in our chart, we have if we have a single component substance, remember we have a line, the vapor line, okay, which divides between liquid, this is P and T, liquid and gas. And then at some point, simply we stop seeing any difference, okay? Everything seems to be the same because they have a very similar density. So this is what we call the critical temperature and critical pressure. So we can put these two guys, Tc and Pc, as a function of the molecular weight of the substance that I have. Okay, because no, it's very seldom the case that my gas is going to be made up of only one component, but actually is going to be made out of several components. Okay, for example, if you have a gas, okay, you typically have gas composition. You typically have the component, and then you have the mole fraction. Okay, so typically you have methane, ethane, propane, etc. And you have a mole fraction associated with each one of them. X, we typically don't use, well, not the letter X, but the letter Z, okay, for that, Z1, Z2, C2, Z, C3. And we know that the sum of all of these sets for all the components are going to be from 1 to n, the number of components, should be equal to 1. Okay, because at the end you should have, all of them should add up to 1. And the molecular weight then of the mixture that you want to use then the molecular weight of the mixture then is going to be the weighted sum of the molecular weight of each component times its molar fraction. Okay, so you have to come up one by one and then sum them up, and then that's going to give you the molecular weight. Okay, and then I will say, well, that the critical pressure and the critical temperature are usually a function of that molecular weight of the mixture. For that, we're going to use a correlation in this course, correlation by Sutton, that he came up with some idea how to predict critical properties using the molecular weight. Okay, but it's not that important as of now. So let's go back to this small detour. Was to now we know that this is the density ratio, so Bg. Bg is the density at standard conditions of gas divided by the density of gas at local conditions. So the density of gas at standard conditions is P divided by Z RT. Okay, and this T should be standard conditions, and Z at standard conditions. And the density of gas at local conditions is P Z RT. Okay, let's see if I didn't make any mistake. Okay, then this guy, because we are talking to pressures, standard condition pressure is very similar to atmospheric. Okay, so this guy is usually typically 1. There is not much deviation with an ideal gas. And all of these other guys, so all of this is a constant, this is a constant, okay, and these are the ones that are really going to be changing. So then my Bg ends up being, the Bg is PSC TSC times ZRT divided by P, and the R is also goes away. Okay, the gas constant. Okay, ZT over P. And this is simply a constant because remember PSC is 1.01325 bar, at least in Norway, and TSC is 15.56 Celsius. Okay, depending maybe some other places in the world you have different constants, but that's what we use here in Norway. Okay, so now we can substitute this Bg back into my IPR equation, which is Qg is equal to 2 pi kh ln of Re Rw 0.75 Then I have this integral, which was from PWF to PR of 1 over mu g bg dp. Okay, and then I substitute this expression into that equation. And what I end up with is, remember, the temperature is simply the reservoir temperature because we are assuming the flow of all the formation is constant. So that also becomes a constant and I can take it out of the equation. Okay, so let's see, I end up with Tc over Psc. Then the pressure comes here, pressure. Then below I have Seth, μg, and then I have here the temperature of the reservoir, the integral of PWF, PR, and dP. 2 pi kh divided by ln Re Rw 0.75. Okay, so that's how our equation, you see that a lot of constants came out, or a lot of constants came out just simply because of the Bg. Okay, if we are defining the Bg with the Z, can assume it's exactly a dry gas. So then we can simply take all of this out of the equation and it becomes simply a constant that is going to contribute to the IPR, to the constant part of the IPR. But now our BO, our fluid related properties, now it looks a bit more now it looks a bit, we know exactly what it has inside, the P, the Z, and the viscosity of the gas. Okay, so let's look at this function, how it looks like with pressure. Okay, because we want to know exactly how does it look like with pressure. So this is P C G, okay, with pressure. And you see that initially, of course, this is 0 because when pressure is 0, is 0. Okay, but essentially we don't start from there, but we start typically from standard conditions. Okay, we start from PSC typically. And then you will see that you have first like a straight part, okay, which is like the low pressure. Then you have a curved and nonlinear part, and then simply it becomes relatively constant. So that's the behavior of the function. Okay, those pressure, low pressure, medium pressure, and this is high pressure. So you see here, if your PWF and PR are in this region, the IPR is going to behave in a certain way. If they are in this region, they're going to behave in a certain way. And if they are in this region, then it's going to behave also in a certain way. Okay, it's going to behave like actually different in these three regions. But of course, we might have that PR, for example, is here, and then PWF is here. So let's look at those cases. Okay, let's look at some simplifications. So for low pressure, we have QG, 2 pi kh, TSC, and that integral actually becomes simply the integral of P, right? So you have P PR squared minus PWF squared. And here I have to put number 2, right? 0.5 here, right? And then I have to evaluate the 1 over C mu g. This is evaluated at P average. Okay, because they are going to change, but it's simply that's similar to the BO, to the undersaturated oil case that we discussed before. Okay, that this part is going to be evaluated at P average. Okay, and you start getting already, if you see this equation and you see the one that the US Bureau of Mines found on the field, okay, you remember C PR squared minus PWF squared, okay, to the power of n, then you see if n equal to 1, then it's a match. Okay, because it's exactly the same. So we see some um, well, actually, yeah, this can be really, here there is a bit of an error, so this can be evaluated at any pressure, okay? Because you see that here the reason for the change in the in the in the slope, okay, the change on those quantities mainly due to pressure because it's linear on pressure. So these guys, they are going to be actually, this is a constant, okay, 1 over mu. In the low pressure, let's make a comment here because I think that's important. Region, okay, then 1 over me gc, this is constant. So actually it can be evaluated at any pressure, okay, at any not at average pressure but at any pressure. And we can pick any one, like let's say we can say reservoir pressure. Okay, low pressure, and this means that PWF and PR should be in that region. Okay, let's go to the high pressure. Okay, and the high pressure region says that essentially that is a constant. Okay, this integral here, this part, it's simply the integrand is actually a constant. Okay, and because of that, simply can go out of the equation. So we have the QG 2 pi KH ln RE RW 0.75. This is DSC, PSC, TR. Again, here now we end up with the integral simply of PWF, PR, okay, of dP. And here we have this 1 over me BG. Okay, the pressure. And this can be evaluated actually at also any because it's constant also, so it can be evaluated at any pressure. Okay, so I can use, for example, I can evaluate at reservoir pressure. So then this ends up with 2 pi kh divided by ln RE RW 0.75 TSC PSC TR, and then I have maybe P reservoir, for example, me set at P reservoir. Okay, and then I have PR minus PWF. Okay, which you see all of this is going to be a constant. Okay, this is a constant, and this guy is the only thing that is changing. So now this is similar to an IPR. This is similar to um, similar to undersaturated IPR. Okay, which was Q oil is PR minus PWF. Okay, they are very similar. And actually you see here this doesn't resemble QG because it's not linear, non-linear anymore, but it's linear, so it doesn't resemble PR, this equation, okay, the back pressure equation. I'm not sure if we called it before, but maybe we should mention it here. This is called the back pressure equation, what these guys made, okay? This is called the back pressure equation. Okay, doesn't, and this one, the one that we found here, doesn't resemble, but essentially the wells that these guys were working with, all of them were low pressure. Okay, so that means that you should be either in this range or in this range.